because Planetary Resources is a venture that was founded in 2009 with the vision to enable off-world mining and exploration through the use of robotics and low-altitude spacecraft outside of the Earth's orbit for the purposes of harnessing these resources and potentially exploring beyond there. Prior to being involved with Planetary Resources, Chris has had a very successful, illustrious career with NASA, where he's earned 2 distinguished NASA medals. He's had an asteroid named after him, 13609 Lewicki, and he was the flight director of the 2 Mars rovers, Spirit and Opportunity. On top of all that, Chris has told me that he is a neophyte Eve player and has done some asteroid mining in New Eden himself. So with all that, I leave you with Chris, and thank you again for giving him such a warm welcome.
All right. Good afternoon, everyone. I'm going to tell you everything I know about asteroid mining today. Should take about 45 minutes. So let me see if the clicker is working. The next button is not doing anything. The black button works. There we go. So our company is founded a number of reasons, but I think the ultimate reason is that we believe that the Earth is where we started, but shouldn't be where we stay. We can expand out beyond that, go into the solar system and into the worlds beyond, as everyone in Eve does. The 3 primary reasons, Stephen Hawking was just quoted recently as talking about we need, as a species, to survive to be a multiplanetary species. And the exploration is really what helps us survive. We've been able to populate the 4 corners of this planet through the use of resources, and we'll continue to populate the corners of the solar system, the corners of the galaxy, by using resources in space and ultimately expanding the relatively finite resources that we have here on Earth into really an infinite set of resources that are in space. So our mission as a company is to identify, to prospect, figure out the right ones, and ultimately mine the near-Earth asteroids, for starters, and we'll tell you a little bit more about those in the talk, both for water and volatiles for fuel, as well as for regular old structural metals and for precious metals. So, all right, the audio works.
Roll 212!
Here's an introduction.
This may seem like science fiction, but today a group of space pioneers announced plans to mine asteroids for precious minerals.
Space pioneers going to mine asteroids for precious materials! Boom, boom! Yes, Stu Beef is all in! Do you know how rarely the news in 2012 looks and sounds how you thought news would look and sound in 2012? The best part, there's no government boondoggle. This asteroid retrieval project is being completely handled by eccentric billionaires.
They are some of the most influential and wealthiest men on the planet. Google's Larry Page and Eric Schmidt, director James Cameron, XPRIZE founder Peter Diamandis, and billionaire Ross Perot Jr.
If you put 2 Google billionaires with a Microsoft billionaires and some astronauts together, you can't go wrong.
So that was about a year ago, actually, about exactly. We actually announced the company to the world a year ago on Wednesday. And we were very pleased. We had 2 success criteria when we launched. One was that people wouldn't make too much fun of us. And if anyone made fun of us, we wanted it to be either Jon Stewart or Colbert. So total success in that regard. So he went on for a full 8-minute piece on the show and made plenty of fun with the theme song, of course. And then I really like how he ended the piece. This one maybe doesn't have the audio. Oh, no, here we go.
I love this story. Well, let's face facts. It seems a little far-fetched. That's why it's a perfect candidate for our brand new segment, Bull or No Bull, with astrophysicist Neil deGrasse Tyson. Let's put 60 seconds up on the clock. Good evening, John. Dr. Tyson.
Good evening.
Dr. Tyson, tonight's question.
Yeah.
Asteroid mining. Bull or no bull?
John, in this case, the answer is no bull.
Amazing.
And John, You know, your opening credits still show the Earth rotating the wrong direction. I'm just saying.
So Jon Stewart actually has fixed the opening credits now. The Earth does rotate in the right direction. So all is well with conservation of angular momentum in the solar system. So we have assembled quite a team to go after the task of space resources and mining asteroids. You heard the introduction from Dave. I've got about 10 years of experience formerly with the NASA Jet Propulsion Laboratory, doing things like landing and operating rovers at Mars. Our founders of the company, co-founders, Eric Anderson, gentleman who is chairman of the Space Adventures, responsible for selling all those millionaire tickets to go visit the space station. The asking price is about $50 million if you're interested, or I think for $150 million you can take a trip around the moon. Tickets may still be available. And the other co-founder is Dr. Peter Diamandis. You may know him as the chairman of the X Prize Foundation. And both Eric and Peter really saw the opportunity for expanding the economy of this planet. If we were going to do that best, and we were going to explore space, the best way was to use the resources of space to help explore space and expand that economy. So we have lots of other people that I've brought with me, other people who were involved in Spirit Opportunity as well as the Curiosity rover, a number of different members from those teams, as well as people outside of the space industry, really to bring maybe what all of you represent in terms of information technology and gaming and really new mindsets into exploring space. But it wouldn't be possible without all of these folks. So Larry Page and Eric Schmidt from Google, of course, and one of their earliest investors, Ram Shriram, Ross Perot Jr., and Charles Spumoni, a two-time spaceflight participant. He was so happy with his first trip to space that he paid for another one. And what I like so much about the support of our investors is they really have the patient and long-term vision that this is an industry worth creating and worth growing. And I think it was said best by Ram Shriram on the bottom when he was interviewing with the New York Times shortly after announcement. He was asked, Ram, asteroid mining, why would you invest in that? What if it fails? And Ram, without skipping a beat, said, well, what if it succeeds? And that's really the mindset that all of our investors have in supporting the company. We have an all-star board of technical, political, legal, and scientific advisors from former Joint Chiefs of Staff and head of the Air Force to legal team to four-time shuttle astronauts to MIT professors, former CTOs of Microsoft. And we're really assembling the best people on the planet that we can to pursue this very audacious mission. So in this next animation, I'll point out a few things. This is the solar system, and you can see Jupiter. Here's the Earth. The Sun, of course, is the bright spot in the middle. And we have the asteroid belt, which I'm sure all of you are familiar with, between Mars and Jupiter. And this is the way the solar system looked in about 1997. And now when we animate it, what you can see is as the Earth revolves around the Sun, you see little flashes of light. And every time you see that pulse and flash of light, that is an asteroid being discovered and added to our knowledge of the population of asteroids that are out there. And in just a few short years, you can see that we've really added from 33,000 asteroids starting out to several 100,000 asteroids. And the space around the Earth is getting quite crowded, and sometimes actually too crowded, as it did last February. But as we end up here in 2013, we now have well over 500,000 objects that we know in the solar system, and almost 10,000 of those which are asteroids that are relatively near to the Earth. So going over the statistics of what's out there, for asteroids that are about 1 kilometer in diameter, it's estimated that there's over 1.5 million of those in the solar system. And we have already found more than 90% of them that are relatively near to the Earth. About 981, actually. So there's maybe about 20 more that we can find in this area. For other asteroids that are smaller than 1 kilometer, about 100-meter-sized asteroids, it's estimated there's about 20,000 of these, and we have found several thousand of them already. But more than just their numbers, for me, really the most exciting thing is how accessible these asteroids are. You might have seen last night the full moon is out there. The moon seems very close. We've sent men to the moon. We've orbited spaceships, and of course, we've landed on the moon. But from an energy standpoint, The moon actually is actually quite difficult to get to. And 17% of the near-Earth asteroids, almost 1,700 asteroids today, are actually easier to get to than it is to send a mission and land it on the moon. And if you want to bring something back to the moon, you've got to climb back out of that gravity well, and that number turns to about over 50% of the asteroids that are out there. So let's take a real quick tour of the solar system and show you some size comparisons of things that are out there. So hope you all recognize home, the blue dot there on the left, and here to scale are Mars, Mercury, our moon, the first and largest asteroid discovered, Ceres, and then the asteroid Vesta. And we'll take a closer look at Vesta. This is courtesy of NASA's Dawn mission, which just finished up orbiting Vesta and has now actually left Vesta and is on its way to Ceres. So here's just an example of how we've gone from a spot of light at night. This asteroid was discovered on the first day of the 19th century, January 1st, 1801. And now, of course, we know it much better than we did at that time, and we can say the types of minerals that are on it. We've actually verified a particular type of meteorite actually has originated from Vesta, and we have samples of those actually in our hands and can compare those things together. So marching down kind of through the solar system, here's another asteroid, 21 Lutetia, which the Rosetta spacecraft flew by just a few years ago. And these are in relative scale with respect to each other. And I'll bring forward all the other asteroids in the solar system that we've explored. And it starts with the very first one that we saw from a spacecraft, 951 Gaspra, only about 21 years ago. This was the first time we had ever seen an asteroid as anything other than a point of light in the sky. And this was from Galileo spacecraft on the way to Jupiter. The next place that it stopped was right past Ida. This is also to scale here. And we found out that Ida actually had a moon orbiting called Dactyl. And just a number of these other asteroids. There's some comets down here in the lower left. Eros was the first near-Earth asteroid discovered a little bit more than 100 years ago, and NASA has put a spacecraft in orbit around that. And if you're having trouble really kind of grasping the size of, how big a 100-kilometer asteroid is, just for reference so you have something familiar, this is the Death Star 2. And if you remember, of course, going through the trench to find the porthole, which was ultimately destroyed, it gives you a better idea of how it compares with Womp Rats and those other things. So I'll point out now this little speck of light up there. Maybe you can barely see it at the laser pointer. It's about the size of the laser pointer dot. This is 25143 Itokawa. And this is the last asteroid that we've gone up and visited up close. The Japanese actually had a mission to this about 6-7 years ago, and they returned tiny bits of sample from this asteroid. And you can see Seattle Space Needle, where Planetary Resources is headquartered, here for comparison. About 500 meters wide, about 200 meters thick. And this is just a fascinating little world. It's got all kinds of interesting things going on it. It's got the characteristic potato shape that, of course, all asteroids must have. There's some physics behind that to explain that. You can see there's very large materials that are kind of hanging on to the edge of it, all kinds of blocky structure. But the other interesting part is it's actually has been grain size sorted, so the very fine materials have gone out to the lowest gravitational potential on this asteroid. So if we had mining technology that could only take big rocks, or we needed big pieces of things, you would know right where to go. If we needed to go after material that had already been crushed, well, nature has already taken care of that. So as I had mentioned just briefly earlier, we know so much about asteroids because meteorites have actually been raining down on us since the planet was a planet. The earliest record of these was actually only about 1 billion years after the Earth was formed in a period called the Late Heavy Bombardment. And that's probably when we got most of our oceans, most of the materials and metals that we're mining today were deposited at that time. And these are things that every time you see a streak of light in the night sky, that is a near-Earth asteroid that it made it through the atmosphere and comes down in the form of meteorites. So we've got a number of different forms of meteorites here, from palezites to howardites to carbonaceous chondrites and metallic asteroids. And I'll talk a little bit about carbonaceous chondrites first from a resource standpoint. So you may be familiar with the 3 basic meteorite types, iron meteorites, stony meteorites, and carbonaceous meteorites. And carbonaceous meteorites, there's some of them that have as many as 20% of their weight in volatiles. And these are volatiles like hydrogen, carbon, nitrogen, and oxygen. And of course, the molecules and elements that those build together form things like water and methane and ammonia. And if you take the hydrogen and oxygen on a carbonaceous chondrite, say a 75-meter one that would actually fit in this hall, you could have enough hydrogen and oxygen to fuel every shuttle launch that has ever been put into space with the rocket fuel that they use, 135 shuttle launches in all. And this is just from one of these asteroids, and of course, I'd said earlier in the talk, there are tens and tens of thousands of these asteroids that are out there potentially for use. In space, you often think about the astronomical distances that we have separating things. So here on the left, you can see the Earth. Over on the right, out in the distance, we've got Mars. The space station is relatively close, just a few hundred kilometers overhead, circling the Earth. And then our communications satellite up in the geosynchronous belt. Higher up, of course, the Moon, 400,000 kilometers away. And all this type of stuff, it seems pretty far away. And it actually is pretty far away. But in space, it's not so much about the distance, it's about the energy. So when you consider these from an energy standpoint in the rocket equation, for people that are familiar with that, it's all about how much energy it takes. And as you can see, it takes a lot of energy to get from where I am standing today to going 7,000 meters per second orbiting the planet. But once I'm there, I'm really, as Robert Heinlein said, halfway to anywhere in the solar system. And all these destinations are very close to each other. So if we can use water and the fuel on it and create fuel stations in space once we get there, now you can take that empty spacecraft that you've set up and you've used all its fuel to get it into Earth orbit, and you can fuel it back up and head wherever you need to go. The platinum group metals are some of the most interesting things that are on asteroids because of the relatively high concentrations. So these are 6 different elements that actually are the rarest elements in the Earth's crust. You may have heard of the rare earth elements, the lanthanides. Well, it turns out the platinum group metals are actually 1,000 times more rare than the rare earths. But in asteroids, because of the way that the planet formed, they're much more abundant in the meteorites that have landed on Earth, and of course the asteroids that are out in space. And if you take a 500-meter platinum-rich metallic asteroid, something about the size of downtown Reykjavik, you'll have the equivalent of all the platinum group metals that have been mined in the history of mining. And there are thousands of these types of asteroids that are in the solar system. The job, of course, is finding the right one. So these asteroids are much more enriched in these elements because of how the solar system formed. And if you could imagine the solar nebula and this hot cloud of gas as it's kind of swirling around and forming, everything is kind of condensing out and settling, and just like a fancy drink at the bar, the light stuff is on the top, the heavy stuff is on the bottom, and the siderophile elements, which means the iron-loving elements, like the platinum group metals, all follow that stuff down to the Earth's core, and that's where most of these materials are on Earth. But of course, on meteorites, there wasn't gravity that allows that to happen, so they are relatively more abundant on the meteorites. So let's look at one particular example. This is one of our favorites in our top 10 list, 2011 UW-158, a name that just rolls right off the tongue. It's an asteroid that is somewhere between 500 meters and 1,000 meters. It's actually something that you can't know this too precisely how these things are discovered until you discover them or study them in much more detail. It has a synodic period, which means how often it goes around the sun when you're aligned that you can send a mission to it, of just under 2 years. And if you take the most efficient orbit to it, you can get there in about 3/4 of a year. And depending whether this asteroid is made of silicates or iron or water, it could be worth as low as only $300 billion. Or as high as 5.4 trillion. So there's a phrase we like to say, the first trillionaires will be made in the business in space resources, and this is exactly the reason why. So there's another part where you may be familiar. Back on February 15th, the meteorite that entered over Chelyabinsk, Russia. And this was caught on dash cams all over the place, and unfortunately injured over 1,000 people from the shock wave that came in, which essentially broke all the window glass in the area. And if you were standing near the window, that's how most of the injuries took place. And this is an asteroid that is only 17 meters across. It would fit on this stage. But when it's going tens of thousands of kilometers per hour, this is something that the amount of energy contained there is the equivalent of hundreds of kilotons of bombs. So it has an enormous destructive power, and these are just the small ones. So being able to mine asteroids and discover and detect them actually gives us, as a side effect, the ability to protect the planet from the hazards that they pose. So we can turn something that is a global scale natural disaster, and for the first time we can't do anything about earthquakes or floods or tornadoes or tsunamis or hordes of locusts, but we have the technology now to prevent asteroid strikes and going the way of the dinosaurs. So from a technology standpoint, in mining asteroids, having participated in several of the missions that landed on Mars, I look at what we are doing on this planet to pursue resources, and am just in awe about it. Deep oil and offshore oil platforms are just incredible, where you build these multi-billion-dollar platforms. You go a mile through open ocean, so out in the North Sea or out in the Gulf of Mexico, and then once you get to the bottom of the ocean, you build a little robotic city, and you go another mile or two down. And sometimes when you're down a mile or two, then you go sideways. And you're working at enormous pressure in terrible environmental conditions. You have to take all of your energy with you because, of course, there's nothing to plug into in the middle of the ocean. There's an environmental risk, as we found in the Gulf a few years back. And then you have to deal with currents and the corrosive salt environment. So in comparison, space, it is a vacuum, but 0 atmosphere versus 1 atmosphere is a lot better than 1 atmosphere versus 300. The physics are fairly straightforward. There's not a lot of weather to worry about. You have 1,300 watts per square meter coming to you from the sun, and the environmental risk in terms of the risk to the planet is nil. It's just out in space, and of course space is just a tremendously huge place. So 5 easy steps for asteroid mining, and actually it's the same whether it's asteroid mining or whether it's mining here on Earth. You have to find where the ore is. You have to prospect and find out where the best ore bodies are. Of course, you then have to establish your rights to use them. You have to extract the materials, and then you have to deliver somewhere where they can be used. So now I'll tell you the story of how in 2013 we are pursuing this. So Planetary Resources, the asteroid mining company, is our vision. It is what drives us. It's the reason why we exist and what we're pursuing. But as I just mentioned, asteroid mining starts with the detection and characterization phase. So we are in the business of building prospecting spacecraft, robotic spacecraft that we will send out into the solar system to not only detect the asteroids, but to characterize them, to go rendezvous with the asteroids and find out which are the ones that are going to be worth building the equivalent of that billion-dollar offshore oil platforms that we can start extracting materials. So we looked at, when we build those spacecraft, how can we do this so that it doesn't cost us billions of dollars to prospect? We've been exploring space for 5 decades at the benefit of the US government, ESA, the Japanese Space Agency in Russia, and now the Chinese. And it's been something that's required government infrastructure. But to go from government infrastructure from privately to privately funded things really requires a way of doing something fairly different. So we want to be independent from that. We also want to be able to mass produce things and do things in really huge scales. So being able to create hundreds of spacecraft per year instead of just one, maybe every 10 years, is something that helps you drive the cost down. If you're only going to make one of something every 10 years, you can be guaranteed that it will be expensive. When we are prospecting in space, we want to do this with costs that are similar for what mining companies and prospecting companies on Earth actually pay to do that on Earth. Something on the order of tens of millions of dollars to make a drill core, go into an ore body, and try and figure out if that ore body is going to be economically viable to build a mine. So if we can do that same thing, the same order of magnitude for costs, we're really kind of in the realm of how business is operating here on Earth. And then last, and perhaps most importantly, to take advantage of where technology has come in the last 10, 20 years, and where it's going to go in the next year, next 5 years, and the next 10 years, is to make asteroid mining as much as we can into an information technology. So with the result of kind of all those driving architecture concerns, what we need to do is make something that is small, lightweight, standard, cheap to get into space, cheap to make. Because we want to make it very small and lightweight, we want to take the subsystems and all the different functions on the spacecraft and use them in multiple ways. To make ourselves independent from government infrastructure and make something small enough that we can send it into space, we're baselining laser communications or optical communications to be able to talk to our spacecraft. As much as we can, we want to put autonomy onto these things, so that we can kind of set it and forget it. And we can tell the prospector, our Arcade 300, to give us the answer. Tell us what the asteroid is made of, tell us what its mass is, tell it what we need to figure out next, instead of sending back reams and reams of raw data. And then as we're doing this, we want to have a mind to the future of where technology is going. Not necessarily where it's been, but be able to predict that in 5 years we'll be able to use a particular type of autonomy, or in 7 years there will be a new type of chip that's coming online, and being able to fold that into our architecture as fast as we can. So we're pursuing this in a program that is much like the program that the United States went through as it was trying to land in the moon in the 1960s. Kennedy got up and gave a speech about landing on the moon by the end of the decade, and when he had done that, we had just barely sent a person into space. We hadn't sent any spacecraft out beyond the Earth's orbit, and we certainly hadn't done anything on the moon yet. So what we started, instead of building an Apollo command module and a LEM and a Saturn V from the get-go, we educated what we were going to need by building the Ranger program and literally sending spacecraft and just trying to hit the broadside of the barn and hit the moon so that we get higher resolution pictures. And then we built the lunar orbiters, which went into orbit around the moon and took very high resolution pictures of the surface. And we used that data to make a landing place for the surveyors. And the surveyors were the first soft landing spacecraft that landed on the moon, which let us know that you weren't going to sink into the moon, into the dust, which is something we didn't even know at the time. And it was that program, the robotic program, that was followed by Mercury and Gemini Apollo, that ultimately got us to land men on the moon. And we see something essentially similar with asteroids. We know a little bit about asteroids from NASA and ESA and JAXA's exploration. We need to ramp up the rate about asteroids. We need to learn more about the resources that are on them, and we need to do so with a capability that can go back to them and visit them for very low costs. So I'll take a quick journey in how technology has evolved in only the last 15 years. Landsat 7, to use an example in Earth imaging, is a imaging satellite from the U.S. government that's about $1 billion. It weighs several tons. It can see a spot about the size of the stage from Earth orbit, and as you can see, it's several stories tall. And if that thing were to fall over, it would surely be in danger of injuring one of the technicians there. Only about 10 years later, there was a private effort which essentially did very similar things to Landsat, but did them with a much smaller, much cheaper spacecraft, and even on top of that, resulted in being able to get better data, even though it was smaller. So here you can start to see Boston Harbor come into focus, see the Boston Museum of Science, and make out some ships there in the harbor. So where Planetary Resources is today is trying to hit this at yet another order of magnitude reduction in both cost and size, and continuing to increase the capability. So this is, as you can see, Boston Harbor, but now you can start to pick out cars, you can start to tell what direction the ships are going, you can see the wakes. And this is just in 15 years, the progression of technology as it's applied to spacecraft. And of course, technology itself, the rate at which it's increasing, is also increasing. It is truly exponential. So to anticipate that in 10 years' time there will be technology that will allow us to more easily explore space and to more easily mine asteroids isn't really a leap of faith at all. It's actually an inevitability. And to position ourselves so that we can take advantage of this advance of technology is the strategy that we have at the company. So here I am in our clean room with a full-scale prototype of what we call the Arcid 100. And this is the first version of what we intend being able to send all the way out to the asteroid. So this small package has the gold barrel on it, which is the optic that allows us to capture those images. We use that same optic for optical communications. We've got propulsion and the structures integrated together, and then, of course, all kinds of goodies back in the avionics bay. And we intend to try these out in low Earth orbit and learn what works and what doesn't, and iterate on that experience in as soon as 2 years. And we just announced earlier this week that we're actually going to take the guts of this stuff, kind of the brains, put them into an even smaller package, and test them out in Earth orbit next year. So to talk about a few of the things that we're doing on the spacecraft, I had mentioned combining optical comm and imaging, and this essentially takes advantage of this very large thing. As you know, with cameras, the bigger the lens, the better, because of diffraction-limited optics. So we want to have one very big lens, and we want to, kind of like you use your SLR, put a different camera body on the back of it when we ever need to be able to do something different. So we've been experimenting with optical comm and working with NASA and MIT in doing some of that work as well. We've got our own manufacturing facility, and here you can see kind of the prototype coming together on the left with the integrated structure and propulsion module, and other technologies that we're looking at putting in are advanced materials, being able to put as much automation as we can. And even if we can't completely automate it at the outset, think of autonomy as kind of a sliding scale. You've got cruise control on your car all the way out to self-driving autonomous cars, and then everything in between, where you had radar and the cruise control that would slow down if you're coming up on a car. This is something that we can iterate and keep adding in bits of technology to get closer to the goal. And then we can use the technology in swarming and essentially using clusters of these spacecraft to explore the asteroids most effectively. So in the process of prospecting, it basically starts from the lower left. Have this graph. You can see the little points of light moving in the sky, and that's most of the asteroids, over 95% of them that are known today. That's all we know about them. We know that they're a point of light. We know that they have a particular brightness. We can make some assumptions about how large they are, and of course we can predict their orbit. And through other techniques, such as taking light curves, we can start to tell maybe its rotation rate. That tells us a little bit about its structure, and even we can put together a shape model of that based on those light curves. If you take a spectra and you break the light into its components, you can put together different curves of that and start to tell whether it's a stony, carbonaceous, or an iron or metallic type asteroid. And ultimately, what we'll do is we'll take the 9,771 asteroids that we know about that are near the Earth today, and we'll down select to our favorite 20. And then our favorite 20 we'll down select to 5, and we'll send missions out to those to be able to tell which ones are going to have the best ore and the best chance of both developing the technology and serving as a resource. So here's just a quick animation that shows the method of using swarm exploration at an asteroid, where we actually do exploration of it with the spacecraft much like distributed computing. If any one of these spacecraft were to fail, you have several others that can pick up the slack. You can see the green portions of this animation represent kind of the near-field communication, kind of like Wi-Fi, and actually may even be Wi-Fi in the way that we'd be implemented. And then that one spacecraft is kind of always pointing at Earth, sending the commands back to home base. We can also, when you're doing cloud computing and cloud observations like this, we can start to do things like, instead of designing a very complex mechanism to excavate material and then process material and then learn about the excavation that we just did, we can actually take the spacecraft, maybe take one of these little guys and do a little kamikaze circuit where we get a running start and smack it into the asteroid. And you have just a very basic shovel where we can excavate material, look at what's underneath, and then continue to do that. So I was looking in the Eve universe and remembering how it was, so in this case, ice mining, and reminded that, of course, you've got a period of it is 10 seconds of the laser cannon doing the mining. And what's kind of interesting about this is, as we've looked into different techniques for processing asteroids, I'd say the laser cannon isn't too far off. mining in space will not be as familiar as mining on Earth. And in many cases, it will be driven by a solar thermal process, where we'll use the energy from the sun to heat and cool and process and ablate and separate materials. So being able to take something like a solar pumped laser and to heat up material and ablate it off the surface, turn it into a plasma, potentially separate heavier weight elements from lighter weight elements, or in the case of ice mining, it's simple as distillation. So taking material, heating it up above the boiling point for water in space, and then that material separating out, and then just like you do with seawater, condensing it back out and cooling it off and having a purified water in space. Or if it's hydrated minerals, going up to a higher temperature and doing much the same. So in space, as I just said, we can use that abundant solar energy, and we can use that really just with technology as simple as mirrors and things that have actually already been demonstrated in space with inflatables. On one of the space shuttle missions, STS-77, there was a large inflatable that was made a very large parabolic dish that had an optical surface on it. So this technology exists, it's actually been tested in space, and are things that we can deploy to be able to concentrate solar energy to help process materials on an asteroid. For the materials that we may eventually consider bringing back to the Earth, and this would be probably just the platinum group metals, and of course anything else that we were interested in scientifically studying, there are a variety of ways of bringing stuff all the way back to Earth. There's very conventional techniques like reentry capsules. There are even commercial capsules that are available today with several American companies now pursuing this capability commercially for NASA. NASA is investigating inflatables to be able to create a heat shield that can literally be an inflatable balloon out of a capsule that you can use to slow down and decelerate a payload and bringing it into the Earth. And we're even looking into things where we can use additive manufacturing or 3D printing and be able to create what I'll call a platinum group metal wiffle ball. And imagine something that has a very low ballistic coefficient that when it hits the atmosphere slows down very quickly, doesn't heat up much, and falls to the Earth's surface at a relatively low velocity, certainly much lower than the meteorite in Chelyabinsk, and with a big range, this is something that you could use those types of technology to land it on the ground. So putting this into, what does this really mean for the future of humanity, and what may exploration and what may our civilization one day look like? I actually think it's a lot like the way it is in Eve. Eve is certainly an aspect of science fiction, but science fiction always has its roots in reality and is just an extension of that reality beyond where we're currently operating. So if you could imagine a space station out at a Lagrange point, relatively near to the Earth, at energetically kind of commonplace, where we have a trading post, where materials and resources come in, maybe passengers, astronauts, government or private individuals, or even tourists, or families who are living and working in space, kind of have this trading post. And between the Mars, between the Moon, and the asteroids, we have kind of just a free-flowing circuit of material and stuff also would eventually make its way down to the Earth. But this is something that little by little, companies like Planetary Resources, companies that are developing capability for modules in space like Bigelow, companies that are exploring and creating exploration capabilities in space like Orbital Space Sciences and Space Exploration Technologies, and the space elevators and all those technologies. These are things that little by little they're moving forward, and this stuff is now possible. Just a little bit, about 8 years ago, a small team led by Burt Rutan and funded by Paul Allen with just a few tens of millions of dollars. Sounds like a lot of money, but with a relatively small amount of money, they were able to put Brian Binney into space. Put him on a suborbital trajectory, and that was something that 45 years before that took the entire United States government and the entire Soviet Union to do, and of course many, many billions of dollars. So this capability is now kind of within reach of private hands, and the engineer who is working today has never had more power at their disposal in their desktop computer, and we've never been able to do more with small, focused teams. So this is something that really will allow resources to be that focus, be that thing that we're going after, to be the economic driver for continued exploration. The asteroids, while there are many out in the main belt, I've pointed out how there are many that are also relatively close to the Earth. We're working on the discovery, prospecting, and claim part of that, of finding the right ones to go out and explore, bringing technology to bear on that, and doing what we can to make this an information science, maybe even make it something that is even a massively multiplayer type effort, where as you're putting in bits of time in the gaming universe, as you're doing things in crowdfunding and crowd science, this is something that I think we're getting to a point where it's not just the governments of the world, it's not just the aerospace engineers of the world that are working on the edge of things. It's really all of us being able to make our contributions in doing that. So with that, I will take any questions that you may have. There's a microphone up at this side of the stage if you want to ask something. And thank you for your attention. Yes, sir.
On the last slide, you actually mentioned about claiming asteroids. I was just wondering what your opinion was on the legalities, considering the Outer Space Treaty doesn't allow claims in space.
Excellent question. So you mentioned the Outer Space Treaty. This is a treaty, of course, that I think over 200 countries have signed. And the Outer Space Treaty was formed in 1967 when the U.S. and the Soviet Union were racing towards the moon. And there was a concern essentially about appropriating land for national use. So as a private company, we don't see any restriction on private means for exploring and claiming resources. And there's actually a lot of precedent that's going on Earth today, whether it be fishing or timber or mining. In many cases, mining companies don't own the mine that they are extracting resources. They have a mineral right. Timber companies don't own the land that trees grow on. They have a right to harvest that timber. And of course, you don't own any of the fish in the ocean until you get them in a net, and then you have a legally defendable right to do that. So while there is not legislation and regulation exists today for regulating an asteroid mining industry, it's certainly something that there are a lot of parallels on Earth that we can extend into space. And there are precedents for doing that. And we see that as we are starting this business, that we'll be able to help lead the development of the appropriate regulation for the establishment of the space resource industry.
With the potential mining of platinum, wouldn't that potentially collapse the market, bringing all the platinum back and thus collapsing your potential profitability in the whole endeavor?
Yeah, that's another common point. If we're going to bring back a 500-meter asteroid that has the equivalent of all the platinum mined in the history of mankind, which actually, it would actually fit on the stage. 6-meter cube on a side is about the sum total of all the platinum that's been mined. So, two answers to this question. One is to just speak directly about when you develop a mine and when you're extracting materials, we wouldn't bring back a 6 by 6 by 6 meter ingot of platinum, land it on the stage in one day, and then flood the market with it. It'll, of course, will take many years to bring this material back to market, and there will be some market adjustments for that. The other thing, actually, is to look beyond platinum and platinum group metals as being valuable because they're scarce on Earth. We like to look at them as being valuable because of their incredible elemental properties. Platinum and the platinum group metals are some of the highest temperature metals. They have excellent catalytic properties. And if we go back 160 years to the time of Napoleon, aluminum was one of the hardest to access metals that we knew of on the planet. And it was so rare and it was so difficult to extract it that when Napoleon would have he would have his royal court, he would serve them off of the gold and the fine china. But when the kings and queens would come and visit, he would serve them on plates of aluminum to demonstrate his power. And that's because it was difficult to extract. And it only took 10 or 20 years after that to be able to make the process of extracting aluminum from bauxite much more efficient. And the market crashed. It went down by a factor of 10, and in another 10 years went down by another factor of 10. But now we're to the point of imagine your life without aluminum. I flew here yesterday in a tube of the stuff. My laptop is made of it, high voltage power lines are made of it, cell phones are made of it, the chairs you're on, this building has got it in the structure. So here's something where we are making a lot more money off of aluminum today than we ever would have in the mid-19th century. So this is something that, of course, we'll have to tread carefully in terms of establishing the market, but there's no reason why platinum should be as scarce as it is today.
Thank you.
Yes?
At the moment, we passively analyze asteroids, so when do we need to adapt our periodic system for new materials we even don't know about?
Well, I would say probably as soon as we get the next mission out to an asteroid. All the minerals in the Eve universe have eerily similar names to the minerals in the real world. But actually, we don't expect to find any new elements while we're out there. But minerals and the combinations of the different elements are something that we're actually finding all the time in meteorites. There are minerals that exist on meteorites that just can't occur on the Earth because of how the Earth forms. So I would say this is almost guaranteed. The real interesting thing will be finding an application for those new minerals.
Aside from waiting for you to launch a Kickstarter campaign, what can we do in the meantime to help you get up there faster? Can we mine you some Eve asteroids and send you the ISK?
Well, I was talking to the developers about that this morning, about maybe what we might be able to do. There's a lot of interesting connections between the data and spreadsheet analysis that you're doing to be competitive in the game. Kind of hearing people tell the stories about really how complex the Eve universe is. It's every bit as complex as the real universe. And a lot of the skills that you're developing and trying to figure out what the best supply chain to get is a lot of the similar things that it takes to figure out what are the right real asteroids in this solar system to go out and find. Part of our thing that we will be doing at Planetary Resources is recognizing, as I think it was Larry Ellison who'd said, that the best people in the world are working for someone else. And there are, I'm sure, a lot of extremely smart people in this audience, and we are looking for ways to be able to allow you to engage in what we're doing. So to be able to pick small pieces of what we're doing and create challenges with prizes and whatnot in parts of our design process are things that we're exploring. And allowing people to kind of take little pieces of what we're doing and turn that into a challenge for a community is stuff that we think actually will help our designs be better. So we look forward to involving people in that way as well. And in the meantime, outside of those things, we are hiring. If people have skills in guidance, navigation, and control, embedded systems, manufacturing, or even business development, or artists, all different types, go to planetaryresources.com/careers. You can fill out our fun job form that asks you a bunch of rude questions, and we'll take it from there.
As far as the materials you'll be mining, such as the platinum ones, for example, these have applications, like you mentioned, as a catalyst, which, as I understand it, is useful in things like technologies such as fuel cells. Is Planetary Resources looking at getting into those sorts of secondary markets as well for the items that it may be bringing in, or technologies that may be created as part of these ventures?
We may. Certainly we recognize that we're creating an industry, and the supply chain is only part of that industry. And if we were to have the world's most successful asteroid mining company, but no market within which to exist, it wouldn't be for much use. So whether it's fuel depots in space, or the use of additive manufacturing in space for creating large space structures, there's a number of partnerships and IP that we're creating related to those types of things. That we may get into, although I expect that many other people will see the opportunity and there will be new businesses formed to take advantage of the new opportunities that we'll have from the industry that we're creating.
Yeah, like some of the examples of that are like memory foam came from NASA, and now it's an everyday item. So
yeah.
Those sorts of things is
yeah,
what I was thinking.
All sorts of derivative technologies. So I think we'll stop the questions there. We're about at the top of the hour. I'll be somewhere nearby if people want to come chat afterwards. But thank you again. Enjoyed the talk. Have a great rest of the conference.